Hello, and welcome to the Software Engineering Institute's webinar series. Our presentation today is Architecture Analysis with AADL. Depending on your location, we wish you a good morning, a good afternoon, or good evening. My name is Shane McGraw. I will be your moderator for the presentation, and I'd like to thank you for attending. We want to make today as interactive as possible, so we will address questions throughout the presentation and again at the end of the presentation. You can submit questions at any time to our event staff. Through the control panel, you'll see a questions tab. Simply type in your question and click send. We will also ask a few polling questions throughout the presentation. These will appear as a pop-up window on your screen. Another 3 tabs I'd like to point out are the Twitter, Survey, and Materials tabs. The Materials tab has a PDF copy of the presentation slides now that you can take today, along with training information from the SEI on AADL. For those of you using Twitter, be sure to follow at Saturn_news and use the hashtag AADL. Once again, it's at Saturn News with a hashtag of SEIAADL. And lastly, the survey will appear at the end of the presentation, and we request your feedback as it's always greatly appreciated. Now I'd like to introduce our presenter, Dr. Julian DeLange. He is a member of the technical staff at the SEI, where his research interests are model-based engineering and improving the development of safety-critical systems by early discovery of architecture and design issues. Before joining the SEI, he worked as a software engineer at the European Space Agency, where he led and contributed to several research projects related to software and system architectures for safety-critical systems. Dr. DeLange got involved with architecture, design, and analysis while designing new methods and techniques to improve the safety and security of critical systems. And now I'd like to turn it over to Julian. Julian, all yours.
Thank you. Thank you so much for attending this webinar. So first of all, I would like to point out what this talk is about. And beforehand, I would like to address a first polling question to know if you are familiar or not with model-based engineering. Shane?
Okay, so you can see the polling question on your question now. And we'll give you about 15 or 20 seconds to vote. So, Julian, you keep on going.
Okay, so this talk is about discussing the actual issue for safety-critical system design and why model-based engineering can help you to design safety-critical system. And after that, we'll focus on how AADL, our technology, can detect issues early in the development process. So first of all, we'll introduce what is model-based engineering and also what are the problems actually with the design of safety-critical system. We'll present a case study and we will apply AADL to verify and analyze a safety-critical system. We will present the system, present the AADL model of the system, and see how we can analyze the architecture. So, first of all, Shane, what are the answers of the polling question?
So let me launch the results right now. Take us a moment. And we got 35% that they already work on projects related to model-based engineering, 4% that are real experts, 34% have read papers but never investigated, and 27% that do not know about model-based engineering. So quite a mix.
All right, so it's quite a mix. So let me introduce what model-based engineering is about. But first of all, where we have issues to design safety-critical systems, if you look at the size of the code for avionics architecture, you see that between 1974 and 2006, the size, so in 32 years, the size of the software increased by 5,000%. The problem right now is you have more and more software components in a plane, and all these components are at different criticality levels. So it poses a problem when you integrate all these components. And this is exactly the problem we find right now. In fact, during the system design, 70% of the errors are introduced during the design, but we find only 3.5% of these errors. So we introduce a lot of errors and we don't discover these errors during the design. On the other hand, during integration, during the tests, we introduce 10% of the errors, but we find 50% of the errors. In other words, we find the errors really lately in the development process, and we introduce these errors really early. So we need to address this issue. And also, what kind of error we find, okay, during the development process? What kind of error we find during the integration? First of all, many global variables, okay, and we have many different interactions, okay. And for example, we have inconsistent values, concurrent access, and what you call the race condition, and so on. Also, we reuse components, and sometimes the reuse policy is not so good, and we have some inconsistency when we integrate the component. We have also some timing issue. For example, the deadlines are not enforced, the worst case execution time is wrong, and so on. So we have a lot of issues we discovered lately, okay? And I think I should not continue the list because I can have a list that is really, really long. Fact number one is that all these errors can be detected at design time, okay? And fact number two, actually, we detect these errors during integration. And fact number three, they incur a lot of rework cost and engineering work. So we need to address this issue early in the development process, not during integration. So we have different technology, and model-based technology will help you to discover this error early. And we have the AADL technology to discover this error early during the design of the system. And that's why I would like to ask you if you already know AADL or not. This is why I would like to know if you are familiar with AADL. Shane?
Okay, so you'll see a polling question popping up on your screen now, just asking if you already know about AADL, and that's going to help Julian kind of where we go with the presentation.
Thank you so much. So why model-based engineering is really important? Because with a model-based approach, you can capture the system elements with a high-level language. And with that, you just focus on what really matters on your system. Time, safety, fault, errors, and stuff like this. After that, you use this model to validate the architecture. So you really focus on what is really important. You check that your requirements are enforced. For example, your end-to-end latency, the different number of errors. You try to detect potential issues from the beginning. And you don't address this error later in the development process. All right. And for that, we have a language called AADL, the Architecture Analysis and Design Language. Are you familiar with that, Shane? What are the answers?
So we got 14% are familiar with it, 45%, let me show in results, 45% that are know the principles, and then 41% have not heard of it.
Okay, so let me introduce what is AADL. So the first version of the language was in 2003, and actually we have the version 2.1. The goal is to define the software architecture and the system architecture, and not only with blocks, but with specialized components. Okay, so we define what is the software, what are the tasks, the timing requirement, and so on. But we also associate that with the execution platform, the processor, buses, and so on. And you can also extend the language with different extension mechanisms, what you call the user-defined properties. User can define their own properties, or an annex mechanism. For example, for safety, I will show you later on in this presentation how we extend AADL to add safety information. So we have a model, an AADL model can have a graphical notation, as I show, with different component types, task, communication interfaces, process, and so on. What is really important is we have right now already a tool set that supports the AADL language and its notation. So let me show you what we have today. We have a full tool set that is called OSATE, and it's an Eclipse platform, and you can create an AADL model directly and edit it. So it's a language, but we also have a tool environment, okay? So let's try to show you how I can create an AADL model, and this is really simple. I create a new AADL package, and I will call it example, all right? And then I can create different component types. As you see on the right of the screen, I have different component types, and I will just make a really simple system with a producer and a consumer. So let me add a process type, okay, and the process will send the data. So for that, I need first of all to make a process that I will call, for example, sender or producer, and I will make a new process, another one, that will be the receiver. So I have two different processes, and what I need after that is to define the communication interface. So I will add what we call a data port, and the goal will be to send the data through this interface. And I can call it data out for the data I'm sending, all right? And in the receiver, I will have to also define a communication interfaces, the out port, and I will call it the in port, sorry, and I will call it data in, and then it's an import, all right? So these two processes are component type, and I can integrate them in what I call a system. So I create a system, and then I will create an implementation, and my system implementation can contain my two component producer and receiver. So if I go inside my system, I can add a first process that will be my sender and a second process that will be my receiver. So I say this is my producer, this one will be my receiver, and I can connect the interfaces. Like this. So it's really simple. In just 2 minutes, I create a model with a sender and a receiver. And after that, I can use this model to start to validate my architecture, okay? So in AADL, we have different plugins in this tool set to validate different aspects of your system. Security, if you have, for example, the producer and the consumer share a different security level, the resource consumption, bandwidth, CPU time, if you associate different tasks to a processor, you will check that you have enough processing time. Also, the data quality and safety and reliability. All right, so today we will use this language AADL to validate a system. So we will try to learn what is AADL and the different concepts and model a system with different variation. And we'll discover potential issues we can find out in the system. So the case study is really simple. It's just a self-driving car. And in fact, you have different devices and different actuators. So we can detect obstacles, and we can also put an alarm for the driver. And also we regulate automatically the speed of the car. So let me also ask you, what would you like to investigate in terms of analysis? For this case study, we have different analysis tools we can use: the latency, the resource budget, and the safety and reliability. That's why we are asking you what you would like to investigate. So the objective today is to help designers to choose what is the best architecture. So for the same system, the self-driving car, we'll propose different architecture variability, different architecture candidates, and then we'll use our tool to analyze the architecture so that you can choose what is the best architecture. And without the implementation, we'll be able to have some measure and analyze the architecture to decide what is the best according to your requirements. So let me introduce what is the system. So this is a functional architecture. On the left side, you have all the sensors, the camera that will detect an obstacle, a radar, speed sensor, 2 speed sensor, and 2 GPS. So the architecture is divided in 3 parts. Sensing with the sensors, compute, we process the value of the sensors, and we control the brake, the acceleration, and the warning device for the driver. So what is important is we have redundancy. The 2 GPS are redundant. Also, if a speed sensor fails, we can use the other one. The same with the obstacle sensor. And from a timing perspective, we are expecting that the max end-to-end latency when we produce the data to the end is at max 900 milliseconds. In other words, when a data is produced by the obstacle camera or the obstacle radar, I want to make sure that the data is consumed by the warning device before 900 milliseconds. From a criticality perspective, let me show you that the GPS is not so important, but the obstacle camera and radar are really important and really critical. That's why in this architecture I have different criticality level. When I control the car, the GPS, it's where is the car, where is my position, and it's not so critical. But detecting an obstacle, also having the speed of the car really matters and is really high critical. For that, we have 2 different alternatives. So first alternative for this architecture, for this system, is to reduce the cost and the complexity. I will only use 2 processors connected on a shared bus. But the problem is, in that case, I have to collocate critical and non-critical function on the same processor. So a non-critical function can impact a critical function. The alternative number 2 is to reduce the potential fault impact. So I will try to collocate non-critical function on a single processor and critical function on other processors so that a non-critical function cannot impact a high critical function. So this is the architecture alternative, number 1. So in this architecture alternative, I reduce the cost and the complexity. So I see that all the sensing functions are collocated on one processor, and all the other actuating function and processor function are on another processor. So I reduce the cost. I don't need 3 processors, only 2, and just 1 bus. And I associate a budget of 50 MIPS on each processor. This is my computing capacity. And then for my bus, I have a bandwidth budget. For architecture number 2, I have 3 processors and 2 buses. So I reduce the fault impact of non-critical function, but also I increase the production costs because I have more processors, so it will be more costly to deploy. And each processor has the other one 50 MIPS, and I have a budget for each bus. So let's have a look at the results.
Yeah, and could we just pause for a few questions too after we
Sure.
show,
Do we have any
show the
questions?
results? We do. So while I queue up the results, first question was from Dawn asking, does AADL utilize state machines with arcs and nodes along with frequency of innovation in interfacing data types?
Okay, so in fact, we have an annex. I point out that early because that we have annex extension, and we can associate state machine in the components to associate the behavior of the system with the state machine. So we have the capability in the tool. So right now, after that, we can already define that and make use of this state machine to analyze the system.
Okay, and then from Mark asking about the demo, does the SCI license this tool? And the real important question, is it free?
All right, so So all what I'm showing right now is available online. We have a model repository on GitHub, github.com. And if you go online on aadl.info/wiki, you have all this, the description of the model, how to get it. The tool is available under the Eclipse public license and is available for free online. Also, all the demo and video today are done with OSATE version 2.0.8, so you can reproduce all the demo on your computer.
Okay, and just one more quickly from Vishal asking, what are the connectors in the diagram?
Okay, so the connector, so we have different interface in AADL, something that we call data port, even data port, and event port. So the difference is data port is only like sampling ports. We just exchange data. Even data port, we exchange data, but also an event. So you have the notion, the concept of an event. It's a new data or not. An event port is only an event without any data. So we have different interfaces. And in this example, I use data port, like sampling ports. The reason why I'm using that is because it's what is currently used in many safety critical systems. We just sample the data. All
okay,
right?
And just to close out the survey, 27% requesting resource budgets allocation, 10% on latency, and the majority, 63% at fault error propagation.
All right, so we'll make a pass quick on the latency. Also, I will show how to use the resource analysis and then focus on the safety tools. All right?
Great.
All right, so some modeling guidelines we are using, because we have different architecture variability. So what we try to do is to factor the model so all the common aspects of the architecture are not duplicated. So we have separate architecture aspects in different files, but what we try to do is to leverage the AADL extension mechanism and try only to capture the different variability factor of each component. In other words, if for the two different variations, what is really important is the number of processors, the number of buses. I can make a generic architecture, extend it, and just add 2 or 3 processors. And we'll use properties, the AADL properties, to quantify the quality attribute of the system. The mixed capacity, mixed capacity, so the capacity of the processor and the software, also the different error types that are propagated in the architecture and so on. So let me show you quickly what it looks like. So for each device, I have a component type. And if you look, I have 2 different speed sensors. And I take advantage of the extension mechanism of AADL to have a generic speed sensor and then refine it with a speed laser sensor and a speed wheel sensor. So I have a common speed sensor that sends the data basically. The interface is exactly the same, but after that I will have a different implementation. I do that with the GPS as well. I have a common GPS and I have 2 different implementations to distinguish the 2 different GPS vendor or GPS implementation. So, as I said before, we have a graphical notation of AADL, but also a textual notation. This is what the textual notation looks like. I will not show all the detail, and please have a look on the wiki description if you want to have a look. Also, we have a video. We will make a walkthrough through the model later. The interface specification, we define the data size for each data type. So the GPS, for example, we say that the size of the data is 50 bytes, a boolean is 1 bit, and the command type to accelerate or brake is 2 bits, basically just a flag. About the organization of the platform, we have a processor, and then we extend this processor ECU with 1 connector, 2 connectors, different bus. For the bus, we associate different properties with the latency budget, the bandwidth capacity. We had also a property to say how much time do you take to acquire the bus or to transfer a byte. Okay, so these kind of information are used when you analyze the system. Basically, the transmission time will be used for the latency analysis. okay? And in the processor, I can say what type of network I'm using with this processor. Basically here, I say this ECU use a CAN networks. For the software, for each function, I have a process. So one software function is one AADL process with one task, what we call the AADL thread. Also, you can see that the AADL process is just a line, and for the thread, it's a dot line. So we also define the communication interfaces. You see in the textual language, we have the feature, okay? And we also define what are the flows. So the feature are the communication interface, and the flow says that if you have a new data coming on this interface, or if you are just transmitting an existing data, if it's just a data flow. All right. So this is the same thing. And for the safety specification, we can distinguish different error types in the system. So, for example, if I have no power, if I have a value error like in out of bound error and stuff like this, if I have no value, for example, if my component die and is no longer working, then I will have no value. Or if I have an invalid value, if my component is failing and is, for example, I have a stuck value. If I have a hardware failure on a processor or a software failure, for example, the operating system. And I can also specify an error behavior with different states. If my component is operational, if the component is failing or not. And I can reuse that. And it's kind of a state machine if you think about it. This was a question before. The initial state is operational, and then I can switch to the fail state later on. And this is error state, and I can add transitions. We can also define the error flow. So in the component, I can define where the error can originate and how they propagate in the architecture. So for the camera, for example, if I look at the device camera, I can say that I use the different error types I showed you before, and the picture can have an error propagation that is no value. In other words, when my camera is failing, I will have no value on the interface. So in other words, it means that I will propagate the no value error to the other component, and the other component will have to take care of it, or it will also impact this component. So if I have no value on the camera, maybe I cannot be able to activate the warning device or to detect any obstacle. So this is an error in my system, and I will be able to make use of it to see the different errors in my system. So in other words, it means my camera, the value will not be propagated. And then I can also describe the in and out propagation and describe the error path. So for example, the obstacle, if I have no value of the obstacle distance, meaning that I don't have the value between my car and the obstacle, it will be propagated and I have no value for the obstacle detected. In other words, if I'm not able to evaluate the distance with the obstacle, I can't say if I have an obstacle or not. It's exactly this kind of thing that will help me to detect the impact of a fault in the architecture, because I will be able to analyze the flows of the architecture. Let me show you the model in a video. So if you import the model on your computer with the tool, you'll be able to have these different files, and you will see that we have the complete AADL textual model with the camera, and we add the properties to describe what is the period of the camera, the compute execution time, or what we call the quality attribute of your system. We also define the error propagation through the interface. For example, the picture, I can have no value. And I add also some properties about the error. So no value means the description is no pictures from the camera. So this is for the device. For the errors, you will see that we have different error type, no power, value error, no value, a valid value, and so on, as we saw before. In the ICD, this is the interface. I have all the different data type with the size of the data, and I will make use of this data on the interface to characterize what are the different data type exchanged between the components. On integration, I have a generic component that integrates all the common components of the architecture, and then I will capture the variability of the system. So I have this generic component, and later on, I define two different variations. One called implementation 1, as we see in this video, or implementation 2. And the difference, as you see, is the number of ECU components over there and over here, and the number of buses. Finally, we have two other files, platform and software. Platform will be for the processors, the buses, and we'll also add some error description, and the software that are all the different processes, tasks with the error propagation added. So when you look at the model, finally it looks like this with the AADL notation. So the graphical view of the model is the following for the architecture alternative number 1. 2 ECU, 2 processor connected through a bus, and all the different software functions bind to either ECU1 or ECU2. For the alternative number 2, what we have between the two is we add another processor and another bus. This is the only difference we have. So right now, what we're going to do is try to analyze the architecture, but do we have any questions?
We do have a number of questions coming in. Johan wants to know, is the OSATE tool qualified for being used in the context of ISO 26262 functional safety?
All right, so it's interesting because the example is a car system. So the ISO 26262 is a standard for automotive system. And as of today, the open source AADL toolset can be used to analyze and validate automotive architecture. On the other hand, we didn't have any qualification status. But I will be glad to discuss that if there is any request to do so and to address that concern.
Okay. Han would like to know, is there a translator from AADL to UML or from UML to AADL?
So there is, in OSATE, there is not capability like this for many reasons. First of all, UML is mostly a graphical language. And we can make, if we make an import or export function, it will be really tool dependent. So we are aware of different initiatives of people that are translating AADL into another notation or importing a notation into AADL. For example, importing a SCADE model or a Simulink model, or also SysML with, for example, tool like Enterprise Architect. The thing is, it's possible. Something else that is really important is there is a profile for UML called Marte, and Marte, we have a good contribution with the UML community to interface UML and the concept in AADL with UML.
Great. Let's get one more from Leonisa asking, do you have security specification to prevent bugs inducing into the system?
To prevent bug in OSATE?
Yes.
Okay. So right now we have a lot of code review on OSATE to make sure that the code does not have any security issue, especially because the code is being deployed in critical environments. So we have this kind of concern right now.
Okay.
All right. Please continue to ask any question online. Shane will address them through the presentation. So let me right now talk about the architecture analysis. So we have this architecture. Again, the example is available online. Please try it, download the OSATE, and try on your own computer and contact the AADL community if you have any question. The community is really active, and I will give you some pointers at the end of the presentation to get support and also more examples. Let me show you how the system analysis works. So I know that a few of you were really concerned and interested by the latency analysis. Let me show you the principle. As we said in the beginning of this presentation, we want the end-to-end latency to be less than 900 milliseconds. Okay, so let's have a look at the flow between in this architecture. So we have a flow for the first architecture and the second architecture, and we can see the different flow contributors. So this flow go from the camera, the obstacle camera, to the warning alert. And in fact, if you have a look, what is really important is the execution time of the different tasks. But they're the same in both architecture. What is really different is the buses, and you see that the transmission time is not the same on both architecture. So the thing is, if we have a look at the analysis tool, and if we have a look at how the tool works, we'll see quickly that what matters is the execution time of the device and also the bus latency associated with the different bus. So if we check the flow latency, the tool will create automatically a report in OSATE. And the report is an Excel report. So you can automatically open it using Excel. So for the first architecture, what is interesting is if you look at the end-to-end latency, remember the end-to-end latency, the maximum was 900. And you see at the bottom that this requirement is captured in the model 900. And for these architecture candidates, the max latency was 886. So this requirement is okay for this architecture candidate. But if you think about it, the difference between the two architectures was a bus. So let's have a look at the impact on the bus in the second architecture. And you will see that between the bus takes more time to be acquired, then my latency is 1 second and 350 milliseconds. So my requirement is not met. And I find only with the model and just by changing a single component, my requirement is no longer met. So you see easily with this architecture description that in the first architecture, the first end-to-end latency is enforced. For the second architecture, I have an issue just by changing a component. If you think about it, the number of times you change a component in a system, somebody say, oh, it does not work, take another component. But you don't think about all the impacts. So with having this virtual integration mechanism, you can detect all this kind of error. Right now, let's have a look at the resource allocation analysis. So remember, we have two different processors in the first architecture, okay? And in the second architecture, we have 3 processors. So what happens if I look at the resource analysis? I will analyze the budget, the processing budget on the processor and also in the task. In other words, my processor has to provide enough processing capacity for my task. So if I have a look at my processor, I define what I call the MIPS capacity that define the processing capacity I can provide to my task. And in my task, what I'm gonna define is the MIPS budget, how many MIPS I need to be executed. And with this information in mind, I can start to make a resource budget analysis. And in my architecture, I can see that, for example, in my first architecture, the total MIPS for the first processor is 54 MIPS, and my processor can provide only 50. So I can't execute this architecture with only one processor. So I have to make a choice. Either I use, I optimize my software, or I use a more powerful processor. The second architecture candidate is okay. With a 3 processor, there is one function that is really consuming in terms of processing capacity, and it's executed on the second processor. So with 3 processors, I'm fine. And all the processor can execute all the tasks. There is no problem on that. So if you have a look at these different architecture, the first one has an issue, and the second one doesn't have any issue at all. So the first one, I have a budget error in terms of processing capacity, and for the second one, I have no problem at all. So let's have a look right now at the safety analysis. We have different safety analysis tools. The first one is what we call the functional hazard analysis, and this is a list of all the errors in my system. The second one is the fault tree analysis. I will show you the top level fault and see all the contributors of this fault. And after that, I will have the fault impact analysis. So I will show how an error propagates into the system. I will show you first how these tools work. So let's have a look first at the fault hazard and impact analysis. So when I do the safety analysis, what I have to provide is what type of fault I propagate into my system. For example, for the camera, this component, I will have to define the out propagation and the error source. So I will say my camera can propagate no value error. I can have no value on my camera, no picture, and this will be an error source. And it will propagate all over the system. But also to generate safety documentation, I need to add some comments, some document where this error is defined, where in the specification, what is the impact, do you have any comments, what is the reference with the other model, and so on. So we add this information. And then when I'm supposed to receive an error, I have error sync. So here for the warning device, I have an in propagation for no value and an error sync. I can say, hey, on my warning request, I have no value. I don't know if I have to issue a warning or not. And finally, I have the error source and the error sync, but I also to define error path. So how the error propagates into the architecture. What I can also do is I can say what I have no value from the camera, maybe it will translate it to an invalid value because maybe I will use the previous value or something like this. So I have to define the different mappings between the error types when I propagate the faults. So in fact, in this architecture, I define the error flows between the different components, and I'm able, with the analysis tool in OSATE, to process this information and use a tool to generate what we call the functional hazard assessment report. It will be a full report available as an Excel document, and I will list all the errors in my architecture. the camera can just propagate the no value error on the picture, the radar no distance, and things like this. Okay, so I have all the errors. In this example, we have only 20 errors, but the fact is when you have a real system, it's thousands of errors. And most of the time, these documents are made manually. Here, it's automatically generated. You don't need to do that manually. So you can update the document as your architecture is evolving. Something else we are doing is to have the fault impacts. It's also an Excel spreadsheet, but it's not only the list of the errors, it's also how they propagate in the system. So the obstacle camera, I can have no value on the picture, but after that, it will propagate in the image acquisition component, and then it will also propagate later on to the obstacle detection, and so on. And finally, eventually, it will reach the warning alert. So in other words, no value on the camera can impact the warning alert, the alert mechanism to alert the driver. So with this simple architecture and these 20 faults, you can see that finally, with only 20 faults, I can have 447 and 45 error paths in my architecture. So one error will have different impacts. And it's really critical because when you are doing this manually, it takes a lot of effort and a lot of time. So for the FHA, what we see is for architecture number 1, I have only 15 errors. And for architecture number 2, 17 errors. The thing is, the difference comes from the number of processors. Okay? In my second architecture, I have more processors. So for sure, I have more faults. But the fact is, I have more processors to isolate in terms of criticality and safety the different functions that are really critical. Right now, let's have a look at what we call the FTA, the fault tree analysis. So the fault tree analysis starts with the top level fault, my warning system or my self-driving car is not working, and then it will show all the error contributors. So I define in my system that my system is failed, the fail state, if I have no brake and if I have no acceleration. So I say my braking system is failing and my acceleration is failing. And then in my brake system, I can define also the reason why the brake failed. So the brake can fail because I have no value on the command. Okay, I don't know if I have to brake or not. I have an invalid value as well, can be an error. And I do exactly the same with the acceleration. In the acceleration, I can explain what are the different errors and why I can be failing. So with this description, I have the top level errors I'm failing, and I can refine and define what are the different contributors and the reason why in the architecture I have this error that is coming. And I can use the AADL model to produce this fault tree with all the dependencies between the different faults. So we have this built-in capability in OSATE, and it generates automatically the fault tree in different formats. One for a tool called OpenFTA, that is an open source tool to use fault tree analysis and to visualize fault tree analysis. Or also we have interface with a commercial tool like Kafka to visualize this fault tree. So I will show you with OpenFTA because it's an open source tool and you can use it at home and on your computer and reproduce this example. When we open the generated fault tree, you will see that finally you think, first of all, that there is nothing. But if you zoom out, you see that in fact, there is so many errors that can contribute to this top level error. So let's zoom into some faults. So what this fault tree analysis tool looks like? I can see that, okay, for example, I have an error from the voter, and the voter can fail because I have no value from the first GPS or no value from the other GPS. So if my two redundant GPS fail, then the position voter will be failing. And I can also associate some probability. And after that, with some fault tree analysis tool, I can make analysis about the probability that my system is failing or not. So I have all the different errors I introduced in my system, and invalid value from the wheel sensor, from the laser sensor, from the camera, and so on. So if I have a look on the FT, on the fault impacts, for architecture 1 and 2, I had exactly the same number of paths, of error paths. The thing, and what we have to consider is that I have the same number of paths, but we have to distinguish the paths according to the criticality of the component. So in terms of safety, the thing is architecture number 2 will be better because we isolate the different criticality levels. For the resource budget, the first one is not the best one because the processor 1 is overloaded. And for architecture number 2, in that case, I can enforce all the resources. What we have to keep in mind also is something else we didn't capture in the model is the cost. In architecture number 1, you need 2 processors and 1 bus. For architecture number 2, you need 3 processors and 2 buses. This is really important because when you have a car, the cost of the processor, the cable, the bus, and so on really matters because you have to produce thousands and thousands of units. In some other safety critical domain, maybe it doesn't matter that much because you only produce a couple of items, a couple of products. So the thing is, the question in the beginning was, what is the best architecture? And the best architecture will depend on your requirement. If you are cost focused or if you really care about safety, resource budget, and so on. In that case, if you are really focused on the cost, maybe the first architecture will be better. And you just have to have a more powerful processor or just to optimize your software. And then the resource budget will not be an issue. So let me conclude first. I hope that this demo give you a good introduction to model-based system design and analysis. So we can see that just with the model, without implementing the system, we can already find many issues that you will find in the integration of the system. So this is new method and new tool, okay? And this is evolving. But this is already ready to use on real projects. And we have several people that are already using this kind of tool to evaluate their system from the specification, where they specify the architecture. The AADL with the specialized component really help you to reason about the architecture. What kind of component are you using? You can add your own property, you can extend the language, and so on. And we have a good workbench to support this language. So we have the graphical editor, the graphical notation, the textual notation, and all these tools are open source and available online. Useful resources. First of all, the AADL wiki. You have plenty of information according many example, case study, and so on. You can access for free online. A book that was written by Peter Filer at the SCI and David Glutch also at the SCI about AADL and the use of the different language features. We have also a lot of blog post series about AADL, and we update the blog post with the new research we are doing at the SCI. We are also really active on the AADL mailing list. The community provides a good support and help you if you have any question. Something else is this month, in Valencia, there is a Models Conference and we have an AADL workshop. It's called Architecture-Centric Virtual Integration. We have a lot of good submission and good paper. The proceedings are already online, and if you want to check them out, please do so. Also, if you want to attend the Models Conference or if you are planning to attend, we would be really happy to see you at the workshop. Thanks, and if you have any question, please let me know, Shane. I hope that we have many questions.
Sure, we got lots of questions coming in for Julian. Just before we get that, just a reminder, folks, before we close out in about 8 minutes to fill out your survey, as your feedback's always greatly appreciated. Julian there mentioned the book. If you go to your materials tab on your console, you'll see a discount for that book available, and also an upcoming training course on AADL from the SCI, so we hope you look into that as well. So let's get into the questions. About 7 minutes left with Julian. Derek wants to know, can AADL be used along with ArchiMate? If you're familiar with that.
I'm not familiar with ArchiMate, so if Derek can send me some pointer, I will be really happy to answer.
Okay, let's move on to Anand. He wants to know, will models add metadata to systems?
Sorry, can you?
One more time from Anand. Will models add metadata to systems?
Okay, so in other words, if I understand correctly, it's what are the metadata associated to the models, right? In that case, this is what we call, what we have with the different ADL properties. And we can capture the different metadata in the different component in the system, or with a different extension mechanism like the ADL annex and so on.
Okay. Johan asks, for the latency calculation, do you support randomization? Can you then model check the results?
All right. So there is, this is really interesting because we have different work for the latency. First of all, there is something with the model checker, and in that case, you have to export the ADL model in a formal notation, like Petri-net or all the formal language, Markov chain, and so on. Thing is, right now, we are not doing that. We are really checking at the high level. But there is many tools that export the ADL notation into this formal language and do so. The thing is, we are the tool that is working on OSATE is a tool that is using the ADL property, so it's a really high language verification, and then you can refine it with appropriate model checker. And we have some users and some companies they are working on it.
And folks, just a reminder, so Julia talked about the OSATE tool earlier. We'll send out our follow-up email tomorrow of where to get the archive and the recording. We'll include that information where they can go and get that the tool for free there. Okay, next question from Yongwei asking, can the end-to-end latency analysis be integrated with scheduling analysis in OSATE? So again, this is something that can be integrated for sure. This is not something that is provided right now in the toolset and available under open source license, but this is something that can be done, and some tool like AADL Inspector from a vendor in France provide also latency analysis, scheduling analysis, and so on. In OSATE right now, we have the budget analysis, the latency analysis that are available. Just a follow-up in case it's relevant here. And this is also from Yongwei asking, does OSATE scheduling analysis support hierarchical scheduling mechanism such as ARINC 653? This is a really good question. So right now, the ARINC 653 can be used for the resource budget. For the scheduling analysis, we don't have scheduling simulation. We have validation, like the tool I showed. But we have also some export to scheduling validation tool like AADL Inspector or Shader or MAST. So this is something that already exists. Unfortunately, it is not available in the OSATE toolset, but the semantics of AADL can provide everything that you need to do so. Okay. From Johan asking, is there an FMEA module planned as well?
Yes. In fact, if you look at the safety analysis tool, what is done by the fault impact is really similar to the FMEA, and customizing the fault impact report will provide the ability to generate the FMEA report as well.
Okay. Rob would like to know, for a system with thousands of signals and hundreds of tasks and multiple processors, each under a safety critical scheduler, 1, how much effort and time is required to set up such a model without being overcome by events, and 2, how hard is it to verify a complex model is correct?
I love this question. I love it. Thank you for asking.
And that was, Robin. Yeah, so yes.
All right. Thanks again for asking. Scalability is a big issue for many model-based tools. And in fact, we have many users that are asking several questions. How scalable is your tool? And second of all, what is the learning curve? And I understand, because when you have to incorporate a new technology, a new language, you are looking at the cost of getting the new technology, how much it costs you, and what are the benefits. We have a blog post on that topic that shows that within a couple of days or weeks, a team of students, master students, were able to acquire the main concept of AADL, to also learn the safety annex of AADL, add safety information, and generate all the documentation for a real avionics system. So we have that on the SCI blog post. You can check out blog.sci.cmu.edu. As for the scalability of the system, some years ago, we have a request from a customer, and the customer have had thousands and thousands of components. And OSATE had a hard time to process that because of many implementation details, for example, the Java heap and so on. And we make a lot of improvement into the OSATE toolset. And right now we are scalable to analyze a system with with a couple of thousand components.
Okay, got a minute left. We're going to do one more question from Julia from Anon asking, are there supporting design patterns in AADL to support analysis and provide proven ways?
Yes, so we are working also on this, and if you look at the AADL wiki, we have a special section dedicated to modeling patterns. So we have different patterns, and with this pattern, we provide different properties, and it's already filled. So you just have to customize the different properties, okay, with your own requirements, and also the different safety aspects and so on. So please check aadl.info/wiki. Thank you.
Julian, great presentation. Thank you very much for your time today. Folks, we appreciate you joining the SCI webinar series. Look for an email tomorrow with some follow-up information on this topic and how to retrieve the archive. Have a great day.
Thank you.